So when each one of these becomes 0, meaning that if you have I is equal to 1, which is 1 degrees of freedom problem, then you have one equation that you need to solve for the equilibrium solution. If the degrees of freedom is 2, then you have 2 equations, because you have differentiate this first with D1, second with D2, so you have 2 equations. So you solve 2 equations to get the equilibrium solutions. To solve for equilibrium solution means we try to get the degrees of freedom. Once we know the degrees of freedom, then we know the solution problem. We know the solution to the problem. So class, this one means you have to solve this. When you apply this, meaning that eventually what we want to solve is a set of algebraic equations, depending on how many degrees of freedom. So you have n degrees of freedom, then you have n equation that you have to solve for the n degrees of freedom. Okay. So that is the actual equation that we need to solve. You need to solve this. So this is partial differentiations of the total potential energy with respect to each of the degrees of freedom. So you get a set of equations that you need to solve. Now, in order to get to know how this is actually being applied, so we will look at one example. Okay, we look at one example. Now, one of the example I have put it on the e-learning that I want you to solve. Okay, so we will look at that example, how actually to solve it using principle of minimum potential energy. Then we will look at more example how to solve. First, we look at actually how it is being used. Yeah? This is being used to solve the problem. So let me go to so on the e-learning, this I give you exercise there, which that is a question that I'm going to use to solve. So in that problems, I think it is a simple problem with now. So before that, I think we need to refresh what equation that we want to solve. So we need to solve starting from this equal to 0, meaning that so this is the set of equation that we want to solve. And the total potential energy is a function of all the degrees of freedom. So these D are degrees of freedom. So this is the things that we need to solve. And of course, then this pi p is equal to UP plus VP. And UP, we have seen for the case of axial deformations, UP is equal to half EA du dx square dx. This is for axial deformations. This is for axial deformations. Then for bending, we have half again EI D2V dx2 square, always the square there, dx. Okay, so this is for bending deformations. Then if we involve twisting, then again half GJ, okay, then d theta x dx square dx. This is for twisting deformation. Okay. So if a structure has axial and bending involved, so this one you have to add up with this. If the structure problem have axial deformation plus twisting, then you have to add up this one and add up this one. Okay. So this is the strain energy if you consider 1D problem. Okay. If you consider 2D problem, then of course it has its corresponding strain energy equations for axial deformations or bending in 2D or they are twisting in 2D. Okay. So we look at the basic concept of solving using 1D problem. Okay. So this is for UP. So all this you have to remember this. Okay. And what are they? All these things you have to remember. And how to find I and how to find J. This is polar moment of inertia. This is moment inertia. Then you have to know if they are giving, if you are giving the cross-sectional area, cross-sectional shape, how to find I, okay, and how to find J. These are all the section properties. So next, one of the things that I like to look at is VP. VP class is potential energy, potential energy of external load. Okay, so potential energy of external load. And this is VP is equal to negative of the sum of all products, okay, of product of what? Product means you have to multiply external load with the product of this and the corresponding displacement. So this is negative of all the sum. So you have to sum up. If you have two loads, then you have to add them up. So, but it is negative of all the sum of all the products of external load and the corresponding displacement, okay, at the load position in the direction of the loading. So this is how we can understand VP. Okay. So if I want to represent that in equation form, okay, then we can write it down in equation form. So it is negative. There must be a negative of the sum of all the products of external load and the corresponding displacement at the location where the external load is acting in the direction of the loading. So that is the definition. So if we want to represent that in equation form, so how do we do that? So let me take away this. So you don't need this, so remember this. So if I have a problem like this, and this is in general, so we always use something like this in general, and there is a loading acting on this problem, and this thing deformed. Okay, you have deformation like this. Then this deformation is caused by, let's say, the loading P1, and then the corresponding displacement here is delta 1. And you have another load here, P2, and the corresponding displacement here is delta 2. And you have another one here, loading acting, P3, and the corresponding displacement at the position where the loading is acting in the direction of the loading is delta 3. So in this case, according to these definitions, so the VP that we need to consider here, this term here, will be negative of the sum, okay, of the sum of the products of the external load and the corresponding displacement in the direction at the location where the load is acting in the direction of the loading. So we have Pi delta I is equal to 1, 3. So this is one. What is the meaning of this? So this is the meaning that we can relate to this by using this example. So in general, Vp is equal to negative I is equal to 1 to n, yeah? Pi delta I. So n, depending here, n is equal to 3. If you have more than 3, then you have to add up again. So the important thing is there must be a negative here. Must be a negative here. Then this is for point load. Okay? This is for point load. If you have, if there is a, let's say in your problem, there is a couple moment. There's a moment acting. Then according to these definitions, you must add that moment, the VP due to that moment. So the moment, if you want to add in this case, yeah, it will be added on negative again, okay, M multiplied with the corresponding rotation. So if there is a moment acting, then you must add up the VP due to that moment, multiply the corresponding displacement for moment is rotation. Okay. So this is how we calculate VP. How we calculate VP. Now, if you have distributed load, this is all point load. Okay, so it is easy to evaluate according to this. If you have distributed load, for example, if there is a problem of beam, okay, there is a beam example, and you have distributed load. This is distributed load. This is point load. So for distributed load, if the intensity of the distributed load is Q, and the range, okay, where the loading is distributed from where to where, let's say is L, the whole range there. Okay. Then for this case, the VP still we based on these definitions, but we need to do integrations. So the VP here will become still negative. It must be a negative there. In this case, because it's distributed, you have to integrate from 0 until where it is acting. If it is a whole range, then L. If it is part of it, then the range only. In this case, L. And then the intensity is tau, multiplied with the corresponding displacement of the problem caused by this. So in this problem, you are going to have V, okay, which is y. The displacement in y direction is the V. Okay. Then integrate. Okay. So this is for distributed load. This is for distributed load. So for point load or couple, point load is like this, or couple, including couple, which is a concentrated moment. So this is how we evaluate. If there's a distributed load, then this is how we evaluate. Okay. So these are the things that you have to know in order that we can solve the problem. Know how to evaluate this and know how to evaluate this. And this one add up will give you this. Then later we differentiate this with respect to the degrees of freedom one by one. So all this VP, UP will be a functions of the degrees of freedom. Function of degrees of freedom. Then we differentiate them partially, okay, one by one. So with this understanding, what is the strain energy equation that you need to use, how to calculate this, then let's go to one example. Okay, how do we actually solve the problem using PMPE? Now, the concept of degrees of freedom, class, I think you should be familiar with degrees of freedom. Okay, how many degrees of freedom? So that is later on because the problem that we want to solve, we classify them as finite numbers of degrees of freedom. So what is the meaning of degrees of freedom? I hope you understand that, the degrees of freedom. Okay. So now we want to solve problems like this, which I already introduced to you. Okay. Which is a problem where you have this waveform. I'm going to use this problem. And these are just two springs with K1 constant, K2. And there is the loading acting. Okay. And we call this point number 1. This is point number 2. This spring 1 and spring 2. So this example is used to illustrate to you the process of solving. Okay? The process of solving. So we want to solve using PMPE. Okay? So the first thing is you need to identify the degrees of freedom. You need to decide the degrees of freedom. What is the degrees of freedom that is corresponding to this problem? So that we need to go back to the definitions of degrees of freedom. Okay? Definition of degrees of freedom. Degrees of freedom is defined as the total number of independent displacement that you need so that you can represent the deformations, the structure at any time. Okay? So how many independent one that you need here? In order that you can tell, okay, this is how it's going to deform. So you get complete information with that numbers of displacement. So that is degrees of freedom. So if you know, if we say degrees of freedom is only 1, then we need to know only that one displacement then we know how the structure deforms. If they say degrees of freedom is 2, then we need to know 2 displacement in order to completely describe how the displacement, how the structure will deform. Okay. So in this case, how many degrees of freedom, which means how many independent displacement do we need to describe, to explain the deformation of this problem? How many? You can answer using SMS. Okay? You can send to one number. If you get the correct answer, then you get some surprise present. Okay. How many you have here? You have a test after this? 2. Okay. This is 2. So the degrees of freedom of this problem is 2. Okay. So degrees of freedom means the displacement, independent displacement. So we need to know the displacement of this point. We need to know the displacement of this point. So that's why the degrees of freedom here is 2. And so that is the first thing that we need to know. Okay. Then we represent these degrees of freedom. We represent these degrees of freedom. In this case, we use corresponding displacement. We say the displacement of this and the displacement of this. Okay, so we are going to use the displacement of this. So I write down here degrees of freedom is. Okay. So when the structure is loaded, I'm going to this is the location before the load is applied, and after the load is applied, of course, these two springs will become compressed. So become compressed, meaning that this one will come down. Okay. And this one also maybe will come down here, depending on what is the K and K1, K2. And this one here cannot move. This one here cannot move. Okay. So this is underloading. This is how it's going to become. Because this one can only move. This one means that this symbol means that it can only move in axial directions. So this is an axial deformation problem. It can only move, it can only deform in axial directions. So this is axial deformation problem. So we need to relate to the corresponding strain energy that will happen and what is the equation that we want to use. So the degrees of freedom that we want to use here will be U1, and the second one is U2. So that is the degrees of freedom, U1 and U2. So if you know this U1 and U2, then you know how the structure, the overall deform, the deformed length or deformed shape of this problem. So that is the things that we need to be able to identify the corresponding degrees of freedom, and this is for axial deformation of the spring. Now we want to solve using PMPE. So meaning that we need to get this strain energy. So strain energy, this is axial deformation problem. So strain energy for axial deformation for spring. Yeah. Spring. So it will be, the first spring is half K1. The deformation of the change in length of that spring. What is the change in length of that spring? This one moved down by U1, this one moved down by U2. So the change in length of that spring is U1 minus U2. But what we want is the change in length. Change in length now. So this is definition of spring. The strain energy for spring is half multiplied spring constant multiplied with the change in length. So the change in length here is this one come down U1, this one come down U2. So the change in length becomes U1 minus U2. And we square it. Okay. This is for the first spring. Then for the second spring, so this is the beauty of energy, we can just add up like this. For the second spring, the change in length will be, originally is here, then this point come down here. So this change in length of this spring from this diagram is just equal to U2, and then you square it. Okay. So strain energy of spring is half multiplied with the spring constant multiplied with the change in length. Then spring number 1, spring number 2, if you have more spring, then you have to add up everything there. So that is strain energy, no more, okay? No more other things that contribute. So next is the potential energy of external load. So the potential energy of external load here, it will be, according to definition class, you must have negative. Look at external load that we have. We have at 1 only, there's nothing at 2. We have 1 here. Okay. So the potential energy is caused by this external load 1 only. So we have P, then multiply with the corresponding displacement, where this P is acting, which is 1 here, in the direction of P. So P is acting at 1, and the displacement of this is U1 in the direction of P, then so you get this. So minus P U1. So now, if settle with this, so pi P is add them up together, this one plus this one, give you the pi P, which is total potential energy. So this total potential energy is this one plus this one, and this, it is a function of this and this. So this is U1 and U2 is the one that we want to solve. U1 and U2 we don't know yet. It's the one that we want to solve. Okay. So let me go here. Let me take away this. Okay. I don't have big enough whiteboard, so I have to take away this. Let me. So pi P is UP plus VP. So you add this thing up. Okay. So the pi P for this problem will become half K1 U1 minus U2 square plus half K2 U2 square minus P U1. Okay. This is the total potential energy, and this one is a function of U1 and U2, which is the degrees of freedom. So it is a function of the degrees of freedom. So that degrees of freedom is the one that we want to solve. That is the solution that we are looking for. So next, by using total principle of minimum potential energy, according to principle of minimum potential energy, this must be equal to 0, meaning that del pi P del U1 must be 0, and also del pi P del U2 must be 0. So 2 equations that we need to solve the 2 degrees of freedom. So once you partial differentiate this, if you partial differentiate this, so what you are going to get will be this one, you get K1 U1 minus U2 minus P equals 0. And the second one, you will get minus K1 U1 minus U2 plus K2 U2. Okay. So you get these two equations. Okay. From this one, you get this. From this one, you get this. So with that, I think then you can solve for the U1 and U2. Then you can solve for U1 and U2 because you have K1 U1 minus K1 U2 equal to P from the first equation. And the second one, you have minus K1 U1 plus K1 plus K2 U2. So these two equations, we solve it together. This one we know, this one we know, this one given, so we can solve this. And this one actually, you can put it in the matrix form. So you solve this, then you get U1 and U2. So P and PE give us directly the solution U1 and U2. These are the two equilibrium equations. These are the two equilibrium equations that we need to solve. Okay. So this simple example, because we use this example because I can show you the whole process. So what is the first thing? And next, how actually we apply the P and PE and what you need to calculate, what you need to know. And then after that, what actually is the final equation that we want to get in order to solve this problem using principle of minimum potential energy. Okay. So this is how we solve this problem. Okay. Now, in principle, if you can extend, I think, more spring, but if you extend more spring here, then you get more degrees of freedom. You get more degrees of freedom, then you need to have the corresponding equations. Okay? And these equations is simultaneous equations, and to solve this is very tedious. Okay? Solving matrix equation is very, very time consuming. So, of course, we can make use of computer or calculator to help us to solve. Once we have the value here, okay, we can solve. So in principle, you end up with equations. Yeah, simultaneous algebraic equations that you need to solve for the degrees of freedom, U1 and U2 here. Okay. Now,